Okay, so let us start the lecture on one-dimensional motion now. Please take notes as I am writing, that would be most convenient. Okay, so these are the topics that we are going to cover. Please see the board. Yeah, frame of reference. Frame of reference is essentially the position from which we observe the system. Okay, most of the times you can say that frame of reference only tells you ki with what velocity is the observer moving. Okay, frame of reference gives you the magnitude and direction of the velocity of the observer. If the observer is accelerating, then naturally acceleration will also have to be given. Yeah. Okay, three types of motion involve straight line motion, that is motion in one dimension. That is what we are going to do right now. This is basic kinematics. Then second thing is two-dimensional motion. In two-dimensional motion, we are going to do circular motion and projectile motion. And three-dimensional motion. Three-dimensional motion, we shall be again referring to circular motion or helical motion. In some sense, helical motion, motion along a helix. I'll show you what a helix is. This is a helix. Okay, motion along some such path. This is helical motion, right? Then we'll be looking at what a position vector is. Let me get this helix out of the way. The next concept is a position vector. Then we'll distinguish between rest and motion. We'll distinguish between distance and displacement, speed and velocity. We'll look at what acceleration is exactly and how to express acceleration in terms of derivative of velocity. Then we'll have to do graphs, position time graph, velocity time graph. And then we'll understand what the equations of one-dimensional kinematics or linear motion are. Motion under gravity is a subsection under equations of kinematics. And then finally we'll be looking at motion with variable acceleration. So that is the topic of today's discussion, kinematics 1. And these are the subtopics. Let us move on to the next slide. Okay, so what is a frame of reference essentially? So look at this tree. Now I am drawing a tree over here. This is a tree, right? Let us say you are an observer and you are watching this tree. Okay, you are looking at this tree. You see this tree over here. Okay, let us say you are another observer who is actually running. Okay, this observer is running in the forward direction with some velocity 5 meters per second. So this observer will also see the tree, correct? But for this observer, the tree will be going back with a velocity of 5 meters per second. Is it not correct? So basically, the frame of reference of this first observer, the frame of reference or the reference frame as we call it in physics, the reference frame of the first observer is stationary. Right? And the frame of reference of the second observer is moving. Correct? Moving with respect to what? With respect to the ground below. We assume for all practical purposes that the earth is stationary and the ground below our feet is stationary and it is not moving. If you have doubts, you can ask. That is not a problem. Yeah. So that is the meaning of frame of reference, the way in which observers are moving. Now sometimes what may happen is this observer might, instead going with 5 meters per second, instead he might be going with an acceleration of, let's say, 10 meters per second square, right? So this is called as an accelerating frame. Accelerating reference frame. An accelerating reference frame is also called as a non-inertial frame of reference. Non-inertial reference frame. And in a non-inertial reference frame, as we'll later see in the topic called Newton's laws, Newton's law of motion, the second law particularly, is not valid in a non-inertial reference frame. Yeah, the difference between inertial and non-inertial is that inertial is going with a constant velocity. Okay, that velocity might be in any direction. Whereas non-inertial is accelerating. Non-inertial reference frames are essentially accelerating reference frames. Alright. So naturally, if this guy is going with 10 meters per second square in the forward direction, he will also feel that the tree is going backward with what acceleration? 10 meters. Yeah, perfect. That's easily understood, right? We have that intuition. Every one of us has traveled using vehicles and trains, right? At some point in time. So tree is also going backward with an acceleration of 10 meters per second square. Fine? Yeah. Let's move on to the next slide. Okay, so we talked about three types of motions. What are they? Mainly one dimensional motion. So 1D motion is like motion in a straight line. The straight line can also be vertical. So the particle is constrained to move along this straight line. It can be either the x-axis or the y-axis or any other line. The line can also be tilted like this. But the particle moves essentially along a line. That is 1D motion. In our syllabus, in 2D motion, we encounter two main topics or two main subcases. One is called as projectile motion, where we throw an object and it falls under gravity on the earth's surface. Okay, the trajectory of the object is called as a parabola, and we will derive the equation of a parabola when we see the next topic in kinematics, which is projectile motion. After we study one dimensional motion, which is mainly the topic of today's discussion, in the next lecture of kinematics we'll be studying projectile motion or parabolic motion. Okay, this projectile motion takes place or happens when any object is thrown under gravity, under the influence of a uniform gravitational field, and the earth's gravitational field is assumed to be uniform. Okay, uniform meaning it has the same value at every point in space. Alright, this is the earth's gravitational field G bar I should write actually, because it's a vector quantity. The second example of two-dimensional motion is circular motion. Okay, when you take a string and tie a stone or a massive object, massive meaning an object that has mass, and you whirl the string around like this, round and round, round and round, the object goes in a circle. The radius of the circle is r, and kinematics of this circular motion involves the relation between the tangential velocity and the angular velocity omega, tangential velocity v subscript t, and the angular velocity omega, and the radius of the circle. We all know that theta in radians is defined as arc length upon radius. This is definition of theta in radians. Definition of angle theta measured in the unit of radians. arc length upon radius. So we can just write S, which is the arc length, which is essentially the length of the arc covered. See, the length of this arc covered. This is arc length. S is equal to r theta. Okay. If we take a derivative of this equation, what do we get? V tangential, that is ds by dt. ds by dt is nothing but V tangential, and this comes out to be r, which is constant because the particle is right now constrained to move along the circle, the circumference of the circle, d theta by dt. And d theta by dt is nothing but omega. So this is equal to r omega. Fine? Makes sense, no? The second one, yeah. V tangential, okay, is defined as derivative of arc length. So the rate at which we are covering the circumference, basically. The rate at which we are covering the circumference. Correct? And ds by dt. So basically r is constant. So constant is taken outside, right? And into d theta by dt. So r d theta by dt. Fine? Makes sense now? So that is equal to r omega. Okay? Yeah. And in three-dimensional motion, we study three-dimensional motion pretty late actually. While we study electromagnetism, we'll study what a helix is. Let me not go into the details of this because this is not required right now. This is a helix, essentially a spring shape. Okay. So these are the types of motions. Okay, while studying physics, we need to acquaint ourselves very well with something called as the position vector. So these are my x, y and z coordinate axis, and this is a point in space, a random point in space P. Okay. So the vector that is drawn from the origin and that joins origin to the point P, having its head at the point P and tail at the origin, this is called as the position vector. We have seen in vectors that this vector can be represented as x I cap plus y j cap plus z k cap, right? This is r bar, or the position vector. Am I correct? Yes. This is the position vector. Okay. So now let us see that there are 2 points. So this point P is point 1 basically. So I'll write a subscript now here. This is x1, y1 and z1, and this is r1. Okay, r1 is the position vector that represents point P. Okay, and there is a second point which is r2. Let's say this r2 represents the second point Q, which has the coordinates x2, y2 and z2. P has the coordinates x1, y1 and z1. Fine. Now the question here is, what is the line segment PQ? How can we denote the line segment PQ to be? PQ, this line segment, how can we denote? Okay, the answer is very simple and straightforward. The line segment PQ, okay, to understand how the line segment PQ is going to be denoted, we note that, look here, I'll draw a vector diagram that is very easy to understand. I will reverse the vector r1, so it will look like this. The reverse of vector r1, that is minus r1, will look like this. Q is as it is. The vector OQ is as it is. Okay, so this is r2 bar and the initial vector is r1 bar. Getting it? Getting it, no? Right. Okay. So according to the triangle law of vector addition, you tell me, this is the tail of vector r1, this is the head, right? And for vector r2, this is the tail. For vector r2, this is the head of vector r2, correct? For vector r1, this is the tail, this is the head, right? So what will be the resultant of these two vectors? From the tail of the first vector to the head of the next vector, right? This is the resultant, no? So this resultant itself is PQ vector, right? PQ vector that starts from P and goes to Q. Isn't it correct? Yeah, exactly. Yeah, so what we can write here is PQ bar is equal to OQ bar minus OP bar. That is equal to R2 bar minus R1 bar. Does it make sense? Okay. So if the final position of the point P is the point Q, meaning the point P moved from itself to Q, or some insect, let's say, moved from the position of point P to the position of point Q. This was the position of point P. The insect moved to the position of point Q. Then it traveled along the vector PQ, which is given as R2 minus R1. Alright. So now we know how to denote position vectors and the algebra of position vectors. Okay. While discussing the next topic, rest and motion, let us ask ourselves, what exactly is the meaning of the word motion? What is motion exactly? Can we try to define it technically? What is motion? So we can define it technically. Motion is basically nothing but change of position. Change of position. Like for instance, there is a dog over here, and that dog wants to move from point A to point B. So position of the dog is changing, right? The position of the dog is changing. Earlier it was at point A, finally it is going to be at point B. So change of position is happening. How quickly it will happen depend upon how fast the dog will run. So it will depend upon the velocity. Okay, how the velocity will change depends upon the acceleration. So basically kinematics is study of motion, meaning how does position change with respect to time. So motion is nothing but change of position with respect to time. Okay, tell me one thing, there is a ceiling fan above us, there is a ceiling fan, right? It's stationary. It has been connected to the ceiling and it is stationary, right? It is rotating right now with some angular velocity omega. But is it position, is the position of the ceiling fan changing? The position of the ceiling fan is not changing, but still can we say that the fan is in motion? Okay, motion meaning it moves, right? So we can still say that the ceiling fan is in motion. Why? When the position is not changing, we can still say that the ceiling fan is moving. Yeah, this dichotomy can be solved by understanding that there is only one point on the fan that is at rest. That is the center of the fan. And this point, the center or the center of mass of the fan, is at rest. That point is not moving. Not moving. But everything else is moving. So everything else is in motion. Okay. So we can't really say that the fan is at rest. we will have to specify that only the center of the fan is at rest, not the entire fan. Okay, only the center of the fan is at rest. Okay, rest is basically absence of motion. Something that is not undergoing motion is at rest. Now this motion depends upon reference frame. This is something that we need to understand. So this is a building, very nice building with glass panes and windows and all. Okay, and we are moving with respect to this building in a car on the road. Hmm? So when we move forward, the building appears to move backward, right? Agreed? Yeah. So basically, when the car moves forward, we feel that the building is moving backwards. So there is motion, right? But at the same time, if an observer is, standing over here, he won't feel that the building is moving. He sees the building and sees that it is stationary there itself. So what do we see? Motion depends upon reference frame, right? So in some reference frame, motion might be happening of some object. Motion of some object might be happening, and in another reference frame, that same object might be stationary. Correct. Okay, distance and displacement. Distance is a scalar quantity or a vector quantity? Very good. Distance is a scalar quantity and displacement is a vector quantity. What is the difference between distance and displacement? Let us say we are here in India. Okay, we are sitting here in Mumbai. Okay, we go to London just for fun because we have some extra cash. We go to London and come back to India. Our distance traveled is 0 or not? Perfect. Our distance is non-zero, but our displacement vector is 0 or not? Yes, our displacement vector has magnitude 0. So basically, what is the difference between the two? From point A to point B, an object moves via some path. The actual length of the path, okay, the actual length of the path, this actual length, entire length of the path is basically the distance traveled. Okay, the actual length of the path is basically the distance traveled. But what is the displacement? Displacement is the vector that joins the straight line from A to B. Makes sense? It is that vector which joins the straight line segment starting from A and going to the point B. The straight line segment. This is our displacement. Okay, so displacement is basically the vector AB bar. This is displacement. I think this is fairly obvious and straightforward, right? This is a simple topic indeed, but we have to go through all the basics. Similarly, what is the difference between speed and velocity? Yeah, speed is a scalar quantity and velocity happens to be a vector quantity. So this is scalar and velocity is a vector quantity. Velocity is given as a rate of change of displacement. Okay, so this can also be written as rate of change of position vector with respect to time. This is velocity, v bar, and speed is basically the magnitude of velocity. Speed is the magnitude of velocity. Now answer one simple question. Okay, is it possible that speed is 0 but velocity is non-zero over a certain interval? Is it possible that average speed is 0 but average velocity is not 0? Is it possible that average speed is 0 but average velocity is not 0? Is it possible? It's not possible, right? Yeah. Because if average velocity is 0, meaning the particle has returned back to the same position or it has not moved at all. There are two possible cases, correct? That the particle has not moved at all. So if the average velocity is 0, what are we basically saying? The particle has moved back to the same position or the particle has not moved at all. Now this is a trivial case. Here speed and velocity both are 0. But if the particle has moved back to the same position, displacement is essentially 0. Hence velocity is going to be 0. But since it did travel some distance, right? Speed is not going to be 0. Okay? Yeah, in the next segment, we will learn what average speed means and what average velocity means. Also, what instantaneous speed means and what instantaneous velocity means. Okay? Instantaneous speed is simple. It is the magnitude of instantaneous velocity. Okay. So, average velocity. So, what is the meaning of average velocity? Let us see. Let us say Aditya starts from point A and reaches his house. So firstly, for about 10 minutes he walks at a speed of 2 kilometers per hour. Then here, from here to here, he takes a train and train goes at a speed of 40 kilometers per hour. This is for 2 minutes and this is for 30 minutes. Alright. So here, what is the average velocity and what is the instantaneous velocity of Aditya? We'll have to see. So instantaneous velocity will have to be calculated in two different segments, right? The first segment of Aditya's motion is this, points A to M. Am I correct? Points A to M are the instantaneous velocity of Aditya between points A to M is 2 kilometers per hour. Similarly, instantaneous velocity of Aditya from M to H is what? Yes, instantaneous velocity of Aditya from M to H is 40 kilometers per hour, right?
Yeah.
Now let us look at average velocity. So average velocity is defined as total distance traveled upon total time taken. Average velocity, the definition of average velocity is total distance, or I should better say total displacement. That would be a more accurate description. Total displacement upon total time. So 2 minutes is how many hours? 2 upon 60 hours, right? 30 minutes is how many hours? Half hour, right? So here total displacement of Aditya, how do we calculate total displacement? Velocity into time is distance, right? And here distance is the same as displacement because it is linear motion in one direction. Okay, so 2 into 2 by 60. 2 into 2 upon 60 kilometers is traveled by Aditya in the first 2 minutes plus 40 into half is traveled by Aditya. These many kilometers are traveled by Aditya. Okay, whole divided by total time. So what is the total time for which Aditya travels? 2 by 60 plus 30 by 60. Alright, makes sense? Total displacement upon total time. So this is equal to 4 by 60, which is 1 by 15 plus 20 upon 32 by 60. Alright, yeah, we are accurate till now. Yeah, so 60 goes up basically, and 60 goes up to give you 4 plus 20 into 60, which is 1200 whole divided by 32. So that is also equal to, divide the whole thing by 4 and you get 300 plus 1 upon 8. If we ignore this one, this is approximately equal to 300 by 8. And what is the value of 300 by 8? It's 300 by 8 is what? 150 by 4, 75 by 2. So it's 37.5 approximately. So approximately 38 kilometers per hour. This is what the average velocity of Aditya. Make sense? The instantaneous velocity was different, right? 2 kilometers per hour was once the instantaneous velocity. Once it was 40 kilometers per hour. But the average velocity came out to be 38 kilometers per hour. So this is the actual definition. This here, right here. This is the actual definition of average velocity. Please note it down. This is the actual definition of average velocity. Total displacement upon total time. Total displacement upon total time. This is the actual definition. Yes. I would like to tell you about the actual definition of instantaneous velocity now. And we have actually seen this also. The definition of instantaneous velocity is a rate at which position is changing at that point in time. Okay, also written sometimes as ds by dt. I'll give you an example. Let us say the position vector of the particle is given as 2t square plus t plus 1 into I cap. That's it. I cap meaning the particle is moving along the x direction, right? At t is equal to 0, particle was present where? At x is equal to 1 meter. Right? At t is equal to 0, particle was present at x is equal to 1 meter. Now if you take the derivative dr by dt, so velocity of the particle instantaneous is equal to dr by dt is equal to, what is the derivative of t square? 2t. So 2 into 2t is 4t. What is the derivative of t? Plus 1. So 4t plus 1 into I cap. Okay, is the velocity vector. Easy to understand, right? So this is the instantaneous velocity. Let us say I want the instantaneous velocity at t is equal to 2 seconds. So instantaneous velocity at t is equal to 2 seconds is equal to 4 into 2 plus 1, which is equal to 9 meters per second. Correct? Now comes an interesting question. What is the average velocity? Average velocity for the first 2 seconds. What is the average velocity for first 2 seconds? Here we'll have to understand what is the total distance traveled in 2 seconds, right? So total distance traveled is nothing but instantaneous velocity into dt, the integration of that upon total time, which is 2 seconds, and the integration has to happen from 0 to t. On integrating, you will realize that you just actually have to integrate this expression, or this is the position vector, right? You have to substitute 2t square plus t plus 1. Once you have to substitute here 2 seconds, and once here you have to substitute 0 seconds. Same bracket, 2t square plus t plus 1. So 1 goes away. After you put 0, these two terms also go away. The answer simply is 2 into 4, 8 plus 2. is equal to 10 meters have been covered in the first 2 seconds. So this whole thing divided by 2 is the answer. Divided by 2 is equal to 5 meters per second. So the average velocity for the first 2 seconds is 5 meters per second. But the instantaneous velocity at time t is equal to 2 seconds is nothing but 9 meters per second, as we see over here. Alright, let's move on to the next concept now. Instantaneous velocity, right? अनिल फोन करत जाऊ नका असं. जेव्हा चेअरची गरज असेल तेव्हा सांगतो तुम्हाला, फोन नाही करायचा असं. Okay. The next concept is that of instantaneous velocity, which we have actually seen right now. Instantaneous velocity is nothing but dv by dt is instantaneous acceleration. Okay. We have already seen this concept, that of instantaneous velocity. dr by dt is instantaneous velocity, right? V instantaneous. Just dr by dt. We have also seen an example relating this. We'll move on from here. Instantaneous acceleration. Yeah, this is an important thing. So again, average acceleration is given as change in velocity v final minus v initial upon change in time delta t, and instantaneous acceleration is given as instantaneous derivative dv by dt. Later we are going to see graphs and we are going to see explicitly how graphically average acceleration and instantaneous acceleration looks like. So here you just need to note right now that instantaneous acceleration is dv by dt, whereas average acceleration is actual change in velocity upon change in time interval. When this change in time interval is very small, this ratio is automatically converted into the derivative of the velocity time graph at that point, and that is the instantaneous acceleration. Okay. Yeah, the next concept is acceleration. Again, we have got two accelerations, instantaneous acceleration and an average acceleration. So dv by dt, the rate at which velocity is changing, that is called as acceleration. That is the actual definition of acceleration that we will be using in subsequent physics. And average acceleration will be given as finite change in velocity upon finite change in time. Okay, I'll give you one problem right now. Let us say a car is moving in the east direction, its velocity changes and it starts to go in the north direction. So the velocity vector is changing, right? Earlier it was moving in the east direction with 5 meters per second. Finally it began to move in the north direction with 10 meters per second, and this change of velocity vector, or the time required to turn the car, this time required to turn the car over here is given as 10 seconds. It took the driver 10 seconds to turn the car. Yeah, the time required to turn the car was 10 seconds. So what is the acceleration? The question is, what is the acceleration? So the solution of this problem goes something like this. Final velocity of the car was 10 meters per second in north direction. Is it correct? Minus of initial velocity is this, right? In the west direction, 5 meters per second, correct? So why am I doing final velocity and then minus of initial velocity? Because I want to find out what is final velocity minus initial velocity, Vf minus Vi. So this is nothing but change in velocity delta V. upon change in time. The change in time is delta t, right? Delta t is 10 seconds upon 10. Simple. So this is going to be our acceleration, right? This is going to be our acceleration vector. So what is the magnitude of this vector? The magnitude of this vector is under root 10 square plus 5 square. So it's under root 125, or that is equal to 5 root 5. So acceleration is going to be equal to 5 root 5 whole divided by 10 is equal to root 5 by 2 meters per second square. Okay, this is one such example. The next topic is position time graph, but before that I would like to give you another example that involves our regular clock. Okay, this is the wall clock that we have here in the classroom. Okay, let us say that here is the seconds hand. This is the seconds hand. All right. So what is the change in velocity when after 45 seconds the seconds hand is pointing at the number 9, correct? After 45 seconds the seconds hand will be pointing at the number 9 if it starts from 12, right? So what is the change in velocity of the tip of the hand? Okay, so this is 5 centimeters long. Okay, so this is also 5 centimeters long. So what is the change in velocity they are asking? What is the change in velocity of the tip of the hand? So how to solve this problem? So question is, what is the change in velocity of the tip of the seconds hand? Okay, solution is, tell me what is the final vector now? Final position vector is what? This, right? Final position vector is this, right?
Yes.
Initial position vector is this.
Yes.
So we have to do final minus initial, right? So minus of the initial position vector is this. So final minus initial will give me what? A resultant that looks something like the green vector. So since this is 5 centimeter, this is 5 centimeter, this will be 5 root 2 centimeter. Okay, and if I set up an xy system over here, this is x and this is y, then this 5 root 2 is in the direction of minus x and minus y, right? Correct?
Yeah.
Okay, so 5 root 2 in the direction of minus I hat minus j hat whole divided by root 2. Why am I dividing by root 2? To get a unit vector. I want to get a unit vector. So this is magnitude and this is direction. So this is delta v. This is my change in velocity. But here we are bothered about only the magnitude of, or rather this is change in position actually, not change in velocity. This is change in position, delta r bar this is, right? And here we are bothered about only the magnitude of the change in velocity. Alright. So we have found out change in position. If we divide it by the time, by the time delta t, what do we get? We get the velocity of the tip, right? So this is velocity of the tip. So if we are taking magnitude, we don't care about the magnitude of the unit vector because it comes out to be 1. The magnitude of this unit vector, this vector, comes out to be 1. So we don't care about that. So change in position upon change in time. So centimeters need to be converted into meters first. So this is going to give us 5 root 2 upon 100. So that is conversion into meters first, into 1 upon 45, right? So this is instantaneous velocity of the tip. Am I correct? Not instantaneous velocity, actually it's the average velocity of the tip. This is the average velocity of the tip. Right. But we have not been asked the average velocity of the tip, we have been asked the change in velocity. It always helps to know how to find out the average velocity, of course, but we have been asked the change in velocity, right? So to find out the change in velocity, we note that initial velocity was like this and final velocity is like this, because initially the hand was rotating towards the right, that is clockwise direction. That is why the velocity of the tip was going like this, right, tangentially. And finally the velocity is going here also tangentially. So ultimately, if we do now final and then minus of initial, what do we get? Final and then minus of initial, we get this direction, right? But direction we are not bothered about, we are only bothered about the magnitude. So let us say the magnitude of these two vectors is v, the magnitude of this vector is going to be v root 2. And this has all happened in a time span of 45 seconds. So delta v by delta t is going to be v root 2 upon 45 seconds. This is the acceleration. And the change in velocity that has been asked, the change in velocity is simply equal to change in velocity here is simply equal to v root 2. Now the question remains that what is v? V is simply equal to r omega, this we have seen earlier, okay, and r is 5 centimeters, okay, and omega is the angular velocity with which this is covering the entire circle. So it covers in 60 seconds, right? It covers 2 pi radians in 60 seconds. So omega is basically 2 pi by 60 root 2. So the value of this is, after converting it to meters, 5 into 2 pi root 2 upon 100 into 60 meters per second. So whatever this answer is our answer. Okay, this question was just a dummy question. The idea was to tell you how to do this clock problem. So essentially we can find the change in position, we can find the change in velocity of the tip of the hand, any hand of the clock essentially. Okay, you just have to do final vector minus initial vector. Usually magnitude is asked, so even if direction is asked, you can find out the direction. Say for instance, here we have found out the direction, right? This direction here we have found out, this direction here we have found out. Okay, all right, good. So this was just a question that we did. Okay, now we come to one of the most important problem solving part of the topic, that is graphs. Most problems are asked from graphs. Okay, graphs and the linear equations, that also will come to. So position time graph, what does this mean? On the y-axis we draw the position. Okay, first of all we are assuming motion in one direction right now. This is what the topic is all about, the motion in one direction. So position, sometimes denoted as x. X is the position basically. Here I am denoting it as s, for the simple reason that the student should not get confused. Okay, and on the x-axis is time. Okay, tell me one thing, at the same time can there be two positions? There can't be, right? So this has to be a function, it has to follow the rules of a function. Okay, at one time there can be only one position. So it can't be one many, but it can be, yeah, so basically y can have multiple values for different times, but not multiple values for the same time. Okay, many one it can be, many values of t can correspond to the same value of position, that's okay. So in this position versus time graph, okay, the slope, okay, the slope gives us what? ds upon dt, which is the derivative, right? We have seen that the geometrical interpretation is of derivative is basically tangent to the graph. So this tangent to the graph gives us slope, right? Is slope, and this gives us the value of instantaneous velocity, the magnitude of instantaneous velocity. So for this graph, the graph that corresponds to velocity versus time will look something like, so initially see positive instantaneous velocity is there, then zero velocity is there, right? In this part zero instantaneous velocity is there, right? So this part is corresponding to here. Then again here also zero instantaneous velocity is there, okay, and here steep instantaneous velocity is there. So higher magnitude of instantaneous velocity. So this is how the velocity time graph looks like. Makes sense, right? Okay, so this is all about the position time graph. Next, let us move on to the velocity time graph. Yeah, velocity time graph basically has two interpretations. Let us say we get this particular velocity time graph, which also goes negative. Okay, then first of all, the area under the curve of the velocity time graph, let us see what that represents. This is the area under the curve, right? This is the area under the curve. It represents integration of v dt. This is the area, actually, this entire area. Okay, let me erase the extra portion. Extra portion we don't need. Yeah. So what does this area represent actually? This area represents integration of v dt. But integration of v dt from starting point or starting time to final time. But this integration of v dt is nothing but what? Displacement, right? Integration of v dt is nothing but displacement. Correct? Yeah. And the slope of this graph is simply going to again represent dv by dt, right? Dv by dt, the magnitude of dv by dt. So that is nothing but instantaneous acceleration. So the area is the displacement, okay, and acceleration and slope is instantaneous acceleration. Please note that the area that is above the x-axis is considered to be positive, and the area that is below the x-axis is considered to be negative. So basically they are going to oppose each other, or it is going to be a higher positive value in this case minus a lower negative value. So this was the graph of velocity versus time. Easy to understand? Yeah, graphs are easy to understand, but many questions are based upon graphs. Okay, there is one graph that is to be also studied, and that is the acceleration versus time graph. Yeah, the acceleration versus time graph. The acceleration time graph basically is going to represent the area under the acceleration time graph is going to represent integration of a dt, and integration of a dt from initial time to final time is nothing but change in velocity delta v. This is vf minus vi. This is change in velocity delta v. Alright. Okay. And the derivative dA by dt is a new quantity called as jerk. So dA by dt is also equal to d square v by dt square, and this also in turn is equal to d cube x by dt cube. So I saw a joke on Facebook once that said don't be a, not joke, I saw a cover photo once that said don't be a d cube x by dt cube. Okay, so this is about the acceleration time graph. Please note it down. Okay, let's move on to the next concept. The next concept is equations of kinematics. Basically, yeah. So basically we have got three equations, and now let us see how all three of them are derived. The first equation is v is equal to u plus at. All the three kinematical equations assume that the acceleration of the body is constant. Okay, they assume that the acceleration of the body is constant. So this is very simple to derive. U is the final velocity, v is the final velocity, sorry, u is the initial velocity, v is the final velocity. So v minus u is the change in velocity, right? Change in velocity. T is the time taken to change the velocity. So delta v by t is equal to the acceleration, right? So this is the definition of acceleration. So from this we can write delta v is v minus u, right? Final minus initial upon t time. T is the time that is required to change the velocity. So this is equal to a. Therefore v is equal to u plus at. Very simple derivation, very simple. Alright, let us look at now the second equation. What is the second equation? S is equal to ut plus half a t square. Now we know very well that S upon t, or rather what we do know is ds upon dt is instantaneous velocity, right? Okay, from initial time to final time. Let us say a particle moves from initial time to final time and covers a distance s with constant, the particle is moving naturally with constant acceleration. Then how can we write the velocity in between initial and final time? We can always write that if the particle starts at t is equal to 0, particle starts at t is equal to 0. Alright, so velocity of the particle will always be given as u plus a into t, right, according to this equation. So ds by dt is equal to u plus a into t. So if I put ds is equal to u dt plus at dt, right, and I integrate this over here like this. So this is from 0 to s, this is from 0 to t, this is also from 0 to t. So the integration of ds just gives me s, the integration of u dt gives me ut, and the integration of at dt gives me at square by 2. That gives me the second equation. The third equation is just obtained by eliminating t from equation number 1 and 2. So simply I put the value of t as s is equal to u into the value of t is v minus u upon a plus a into v minus u upon a the whole square by 2. Now after you simplify this equation, you will get v square minus u square is equal to 2as. This is what you will get, or v square is equal to u square plus 2as. This is our third equation, and this is the derivation of all the three kinematical equations. Makes sense, right? 1, 2 and 3. As a student of physics, you should always be able to tell how these three equations have been derived. Alright? Next is the concept of motion under gravity. Yeah. So let us do that with an example. Now to solve kinematical questions, what we need to do is we need to set up a coordinate system. So usually we set up this xy coordinate system where positive x direction or the rightward direction is considered to be positive x direction, upward direction is considered to be positive y direction. Okay, and we have to substitute the values of velocity and position into our formulas: velocity, position, displacement, acceleration, along with signs. For instance, Aditya is standing over here and Aditya throws a ball up in the sky. This building is 100 meters tall. How much time is going to be required for the ball which was thrown at 5 meters per second to land on the ground? This is our question. How much time is going to be required for the ball which was thrown with 5 meters per second to land on the ground? What equation do you suggest we should use? Equation 1, 2 or 3? This is motion under gravity, right? Naturally, the acceleration due to gravity is g. Third equation? No, second one, right? Because time has been asked, so second equation has time. Correct? Yeah. So S is equal to ut plus half at square. Now look here, S is minus 100 because 100 is towards the negative y direction, right? From the starting point we have to measure in the negative y direction to measure the final position, right? So instead of S we'll substitute minus 100 is equal to u is positive naturally, 5 into t plus half into g. G can be assumed to be 10 right now, 10 meters per second square, that is the acceleration due to gravity, into t square. Alright, so g by 2 again is 5. So basically what we get is t square plus t plus 20 is equal to 0. So 20 can be said to be, okay, this equation can't be easily factorized. We'll have to use the quadratic factor formula equation, minus half plus minus b square minus 4ac whole divided by 2. So 1 minus 4 into 20 root of that whole divided by 2. Apparently we are getting complex answers. Okay, that's fine though, the numbers that we chose were arbitrary anyway. So basic idea is this: you will get a quadratic and you have to solve for time. Alright, is the equation correct? Okay, see here we have made a mistake. Let us solve this problem again, because we have made a silly mistake here. This is the equation that we are going to use, correct? So S we have understood is in the negative direction and S has to be substituted as minus 100. So this is equal to ut, which is 5 into t plus half into g is also downward, no? G is downward, right? Acceleration due to gravity. So this is minus 10, not 10, it's minus 10. Now we'll get correct answers, proper answers, into t square. Alright, so This can now be simplified as 5t square minus 5t minus 100 is equal to 0. Alright. So t square minus t minus 20 is equal to 0. Minus 20 can be written as minus 5 plus 4, right? Minus 5t plus 4t. So t minus 5 and t plus 4, okay, is equal to 0. Therefore t is equal to 5 seconds, or t is equal to minus 4 seconds. Minus 4 seconds is a value that has to be discarded because time can't be negative, and we simply use the value t is equal to 5 seconds. This is the answer. This is when the object will reach the ground. Correct? So this is an example of motion under gravity. In the problem aspect of it, the problem solving aspect of it, we'll see these are the problems. There are about 30 questions. We are going to be doing these 30 questions in this lecture only. Okay. So this is motion with variable acceleration. But in the problems, we'll do more questions about motion under gravity. So what is the meaning of variable acceleration? An example simply will be 2t square, or let me put something like, I should not put 2t square. A is equal to alpha t square plus beta t plus gamma. So the acceleration is changing with respect to time, right? So now let us say somebody asks you, how much is the distance traveled in the first 5 seconds? Alpha has a value of, let us say 2 meters per second raised to 4. The units have to match, so alpha, beta and gamma have to have appropriate values. Beta has a value of 5 meters per second cube, and gamma has a value of 10 meters per second square. Okay, now the units will be of acceleration of all the terms on the right hand side. Dimensional analysis tells us that all the units on the right and left hand side should match of any physical equation. Alright, so acceleration now after the units are taken care of is simply 2t square plus 5t plus 10, right? This is our acceleration. Now the question that has been asked is, how much distance does it travel in first t seconds, or first, let's say, 5 seconds, given that it starts from rest at the origin. Alright, it starts at rest at the origin. Huh? Yes, we'll have to do integration firstly to get the velocity. Okay, so let us do first integration and let's see how it proceeds. So integration of a dt is going to give you the velocity time relation. So that's equal to 2t cube by 3. So that's 2 by 3 t cube plus 5t square upon 2 plus 10t. Alright. So this is from 0 to t, right? So if you substitute 0 and t, you get the same thing back. 2 by 3 t cube plus 5t square by 2 plus 10t. Because it starts at t is equal to 0, no? At the origin. At t is equal to 0. In the question we have to add that. So now we need x versus time, right? X as a function of time is nothing but integration of v dt. Again, time is from 0 to t. So the integration of this thing again now. So it's going to be 2 upon 12 t raised to 4 plus 5 upon 4 t cube plus 10 upon 2 t square. Correct? This is going to be the answer. So x as a function of time is this. So how much does it travel in the first 5 seconds? Okay, so instead of 0 to t, if we put 0 to 5 over here, then we have to substitute the limits of 0 to 5 here, right? And then whatever is the answer, namely 2 into 5 raised to 4 divided by 12 plus 5 into 5 raised to 3, 5 raised to 3 divided by 4. So total it's 5 raised to 4 actually here also, plus 10 into 5 square divided by 2. So whatever is the numerical answer is the answer to our question. Correct? Okay. Now let us move on to the problem solving aspect. A particle moves along a straight line such that displacement at any time t is given by s is equal to t cube minus 60 square plus 3t plus 4 meters. The velocity when the acceleration is 0 is what? How to do this? They have asked what is the velocity when the acceleration is 0. So firstly we'll have to find the expression for acceleration, right? So acceleration is given as ds by dt and the derivative of that also. Dash, let me write, dash is derivative. That is d square s by dt square. So this is equal to 3t square minus 12t plus 3 and the derivative of this whatever I have written is the first derivative, and again taking the second derivative, 60 minus 12, that's the acceleration. So putting this is equal to 0, we get t is equal to 2 seconds, right? So at t is equal to 2 seconds, what is the velocity that is asked? So velocity is the first derivative, so velocity is 3t square minus 12t plus 3, no? Right? This is the velocity. And what is the velocity at t is equal to 2 seconds? V is equal to how much? V is equal to 3 into 4 minus 12 into 2 plus 3 is equal to 12 minus 24 plus 3. So this is equal to minus 12 plus 3. So this is equal to minus 9 meters per second. Okay, this option. Oh yes, meters per second, of course. Meter per second, not square. The next question is again simple. A body moves 6 meters north, 8 meters east and 10 meters vertically upward. What is the resultant displacement from the initial position? Alright, so let us say I draw the grid like this. This is the north direction, this is the east direction. Okay, this is the east direction. So naturally this is south and this is west. So a body is going to move what? 10 meters north, towards the north it will move. 6 meters towards the north it will move. Then 8 meters towards the east it will move. And 10 meters vertically it will move, right, out of the plane of the paper. So first of all tell me what is this displacement. 6, 8 and 10 form a Pythagoras triangle, right? So this is 10 meters. AB, C, D is the path that the body takes. Body goes from A to B to C to D. Alright, alright. Okay. Smaller line, different color. Yeah. So this green thing that I have highlighted, the magnitude of the green thing is 10 meters. And the path that the body takes is actually shown in red. This is the path that the body takes. Okay. Now, if we only look at triangle ACD, what we will see is in triangle ACD, what we'll see is this is 10 meters and this is also 10 meters. So this has to be 10 root 2. According to Pythagoras theorem, this is 90 degree. This is the answer. A. Alright. Shall I move on to the next question? Okay, a particle is moving along the circular arc of a circle. This is a circle, and the particle is moving along the arc of a circle like this. Particle is moving along this arc, let's say. All right? Yeah. So what have they asked? It moves through an angle theta. The magnitude of displacement is what? The magnitude of displacement. Okay. So basically, displacement is this line. Let me draw it clearly. Let me draw this diagram clearly. So displacement is this line. What is the value of this line they are saying? So if it moved through theta, then this is theta by 2, right? And this is r. A, B, C, D. Displacement is nothing but BD. BD is equal to displacement. Alright? And the given angle is theta by 2. CAB angle is theta by 2. So basically BC is simply equal to R sine theta by 2. BC is R sine theta by 2. So BD is nothing but 2R sine theta by 2. Because these two triangles are congruent, right? ACB and ACD are congruent. Using what? Hypotenuse side test. AD is equal to AB. AC is the common side. So hypotenuse and side are common in two right angle triangles. So they are congruent. So basically BC is going to be equal to DC. So BD is equal to 2 times BC is equal to 2R sin theta by 2. So what is the answer? 2R sin theta by 2. This is the answer. A. Okay? Easy to understand this question? The ratio of numerical values of average velocity and average speed of a body is always. So they are asking what is the ratio of the magnitude of average velocity and the average speed. What can be greater? Average velocity is greater or average speed is greater? Obviously, na? Speed can never be less than velocity. Never ever. Speed can never be less than velocity. I'll give you an example. Let us say the object starts from here and comes back over here. So the average velocity is simply this distance divided by time. So average velocity is simply distance AB straight line distance divided by time. This is velocity average, the magnitude of velocity average. But speed x, y, z, w, speed is nothing but the entire path length a, x, y, z, w, b, the length of this entire path whole divided by time, right? So since distance is always greater than displacement, yes, the values of average velocity and average speed, the ratio of numerical values is going to be unity or less. They can be equal or less than 1. Perfect. That's perfect. Next question. A particle moves along x-axis in such a way that its x coordinate varies with time according to the given equation. So what is the initial velocity of the particle? Initial meaning at t is equal to 0. Okay, very easy question. Dx by dt is velocity, right? So dx by dt is given as minus 5 plus 12t. Correct, no? Minus 5 plus 12t. So at t is equal to 0, they have asked. At t is equal to 0. So we put t is equal to 0 in this equation, no? So this gives us what? Minus 5 meters per second. Easy again? This is the answer. Okay. Car travels a distance s on the straight road in 2 hours and then returns to the starting point in the next 3 hours. What is its average velocity? Okay. Can you say? A car travels distance s on the straight road. S distance it travels 2 hours. They are tricking you here. They are tricking you here. This said distance in 2 hours and this backward distance in 3 hours. What is total displacement? Tell me. Total displacement is what? Zero, no? So average velocity has to be, of course. So the answer is none of these. They have deliberately not given the option 0 over here. Otherwise, students will think about the option 0. They don't want to prompt the thinking of option 0 in the minds of students. That's the idea. Correct? Good. But let us say they have asked us to find out the average speed. Then what will we do? Average speed. Finding out average speed in this problem is a good, exercise. See, average speed is total distance traveled, s plus s. Total distance is s plus s upon total time taken. So that is 2 plus 3. Yeah. So 2s by 5. This is average speed. Okay. But here they have asked average velocity. So the answer is 0. Because the particle or the object returns to the object, here is car. So it returns back to its original position. Okay. By the way, all these objects we are taking it as point particles right now. That's understood. Okay. A particle moving in straight line covers half the distance with speed 3 meters per second. Other half distance is covered in two equal time intervals with speed 4.5 meters per second and 7.5 meters per second respectively. The average speed of the particle during this motion is, so basically d by 2 distance is covered with what speed? 3 meters per second, right? Then again this d by 2 distance is split into two distances, one that is covered with a speed 4.5 meters per second and one that is covered with 7.5 meters per second. So total distance covered is d. Am I correct? Total time taken is, what is the time taken for this? Time taken is equal to distance upon velocity, right? So d by 2 divided by 3. So this is the time taken for the first one. Okay. Now plus time taken over here is what? Okay. No, what? Yeah, correct. You have to do something like this. So this distance d by 2 is again split into x1 and x2. So time taken for x1, let it be t1. So x1 upon 4.5 is going to be equal to t1 and x2 upon 7.5 is going to be equal to t2. Alright, total time is d by 2 into 3 plus t1 plus t2. That is the total time. Okay. Also x1 plus x2 is equal to d by 2. Correct? This you have understood. X1 plus x2 is d by 2. Okay. So how do we go about solving this now? So instead of x1, okay, another relation also actually we have another relation, that 4.5 t1 plus 7.5 t2 is equal to d by 2, right? But that's not really giving us something new. Okay, look here, this data we are ignoring. That's our problem. The other half of the distance is covered in two equal time intervals. Two equal time intervals, right? So what is it? T1 is equal to T2 basically. Okay, this is something they have given. It's very useful. T1 is equal to T2. So T1 is taken as common outside. Okay, and 4.5 plus 7.5 is equal to d by 2. So T1 is basically equal to d by 2 into 12, correct? And here we want T1 plus T2. So that is 2T1 we want, right? So 2T1 is equal to d by 12. Do you get it? So this is going to be average speed. For clarity, I'll write down the formula again. The first part is covered in time t naught. The second part and the third part of the motion require time t1 and t2. Time t naught is given as d upon 2 whole divided by 3, which also has been written over here. Time t1 is equal to time t2 according to the problem statement, and time t1 and t2 both have been found out to be equal to d upon 24 and d upon 24. Adding them, we get a value of d upon 12, and this value d upon 12 has been written over here. So while finding out average speed, now we just cancel the value of d, and the answer that comes out is 2 upon 1 whole divided by 2 upon 12 plus 1 upon 12. So that is 3 upon 12 in the denominator. That is 12 upon 3, that is equal to 4 meters per second. This is a useful and important numerical to grasp. Alright, easy? Yeah. So the answer is this. Okay, let's move on to the next question. Okay, let's read the question. The displacement is given as, what is the displacement given as? X is equal to t plus 1 square, right? In such situations, we are obliged to understand that the units are taking care of themselves. So basically there is some constant multiplied over here, okay, and the constant takes care of the units appropriately. Which of the following statements about its velocity is true? So velocity is dx by dt. So this is equal to 2 into t plus 1 is equal to 2t plus 2. So velocity is not constant. It's not zero. It's not constant. It increases with time. That's true. It decreases with time. That's false. So C is true. Okay. Easy question. 8. The correct statement from the following is, a body having zero velocity will not necessarily have zero acceleration. That's true. That's the correct statement. I'll give you an example. If you throw a body up into the air, at the highest point, acceleration due to gravity is still being applied on the body, right? But it has zero velocity at the highest point. So clearly the first option itself is correct. So we don't even need to check the other options because they are going to be wrong. You can check if you want later. Okay, but they are going to be wrong. This was a qualitative question. A car decelerates at a constant rate during a speed commencing at t is equal to 0. Which of the displacement time graphs represents the displacement of the car? So the car is going to decelerate at a constant rate. So this is a displacement time graph, right? So displacement time graph for acceleration looks like this. Because S here is proportional to t square. So during deceleration, displacement time graph is going to look something like this, because negative acceleration. This is deceleration. Which of the displacement graph represents the displacement of the car? Yeah, the answer is actually D option. Now here S is proportional to minus t square. Minus t square will look something like this, right? T square will look something like this. Minus t square will look opposite, ulta uske, kuch to, right? Downward facing parabola. Alright, so the answer is actually D option. Okay, which of the following velocity time graphs is not possible? Okay, velocity versus time is possible, they are asking. Is possible. Yeah, at the same time particle cannot have two velocities. This we know. So this graph and this graph are discarded only. This is possible. This graph is discarded because see, look here, at the same time particle is having two velocities. 3 in fact, according to the graph. The graph below shows the velocity versus time of a body. Which of the following graph represents the corresponding acceleration versus time graph? Okay, so here the acceleration is a negative value, right? Because the slope of velocity time graph in this particular region is negative, this region. Alright? And here the slope is positive. So here the value is going to be negative and here the value is going to be positive. So something like that, this is the acceleration time graph. So which is given by only this option. Correct? So all other options are wrong. 12. Two cars A and B are at rest at the same point initially. A starts to move with a uniform velocity 40 meters per second. B starts in the same direction with constant acceleration 4 meters per second square. Then B will catch A after how much time? So when B catches A, half into 4 into t square using the second equation, okay, has to be equal to 40 into t. Okay, because when they catch, they cover equal distance, right? So 2t has to be equal to 40. So t has to be equal to 20 seconds. Very easy, straightforward question. Typical. Yeah. So let's go to the next question now. A car is moving. A car is moving with a speed of 40 kilometers per hour and can be stopped by applying the brakes after at least 2 minutes. 2 meters. Okay, 2 meters. So distance required is 2 meters to stop the car. If the same car is moving with a speed of 80 kilometers per hour, what is the minimum stopping distance? Okay, so final velocity is 0 in both the case. Initial velocity u square minus 2as. Why minus? Because retardation is being applied, right? Retardation is being applied, that's why minus. Acceleration is negative na while stopping the car. So here initially 40 diya hai. So 40 square upon 2s or 40 square upon 2a is equal to 2. Similarly they have asked कि 80 अगर होगा तो 80 square upon 2a is equal to what? Okay, yeah. So if we just take the ratio, question mark divided by 2 is equal to, now how much distance is required they have asked? 80 square divided by 40 square. So this is actually 2 square, which is 4. So question mark is equal to 2 into 4 is equal to 8 meters. Alright? Yeah. The next question. An engine of a train moving with uniform acceleration passes an electric pole. This is the electric pole. Okay. Today there are no crows sitting on it. So engine of this train, this is the engine, the first part. This is the train. So the engine passes with velocity u and the last compartment with velocity v. When the last compartment passes, right, of the train, this passes with velocity v. The middle point of the train passes with what velocity? So this train is supposed to be accelerating with some acceleration a in the forward direction. Correct? Let the length of the train be L. Okay. So basically last part, when the last part passes, train has covered a distance of 2L. Do you see? Because this much L train has covered. And also the train has been located over here, no? The train is now located over here. So when the last part passes, the train has covered this much forward distance because now the train is located over here. So this much forward distance the train has covered. So first wheel of the train comes over here. So the distance covered by the train is L, right? Yeah. So basically what are we getting? V square is equal to U square plus 2A length of the train. This is what we are getting. Okay. And when the middle is passing, this is L by 2, right? So V is equal, V middle square is equal to U square plus 2A L by 2. Correct? When the middle passes. Yeah. When the middle passes, L by 2 substitution we have to do, right? So this is equal to U square plus 2A. Instead of L, what can we write? V square minus U square upon 2A whole divided by 2. L by 2 may I have just substituted L. So 2A goes away. What do I get? This is equal to V square by 2 plus u square by 2. Actually, when you simplify it, it comes out to be v square by 2 plus u square by 2. So that is option C. How does it come out to be that? Because this is, I'll do it here, u square plus, this is equal to u square plus v square minus u square by 2, no? So this is equal to u square minus u square by 2, okay, plus v square by 2. So u square minus u square by 2 is what? U square by 2, okay, plus v square by 2 is equal to u square plus v square by 2. Okay, yeah. Shall I move on?
Yes.
Yeah, a point moves with a uniform acceleration, and v1, v2, v3 denote the average velocities in the three successive time intervals t1, t2 and t3. Which of the following statement is correct? So the acceleration is going to be uniform. So acceleration is basically change in velocity upon change in time. Alright, so v2 minus v1, so this time interval the particle moves with a velocity v1, this time interval is t1, here it moves with v2, time interval is t2, here it moves with v3, time interval is t3. Alright, and the acceleration is the same. Acceleration is the same, correct? And these are the average velocities. These are average. Acceleration is what? Final minus initial. Alright. So what are they asking us to compare? They are asking us to compare change in velocities upon change in time. This is what they are asking us to compare. Correct. So here there is a plus option. This plus time will not be taken when velocity has a negative option, right? Here both the things are plus. This is also not correct. And here they are taking the time 1 minus 3. v1 minus v2, v2 minus v3 to 1 minus 3. 1 minus 3 are completely not related, right? t1 minus t3, completely unrelated. Basically, what are we going to get? We are going to get something like v1 minus v2 corresponds to t1 minus t2, or change in velocity v1 minus v2 is equal to a times t1 minus t2. Something like that we are going to get, right? Okay, because change in velocity upon time interval is acceleration. Similarly, v2 minus v3, change in velocity, will also be equal to a into t2 minus t3, because acceleration is constant.
Yeah.
So taking the ratio, we get option D as the correct answer. You just take the ratio of these two things. Option D is the correct answer. Alright, next. Yeah, two cars A and B traveling in the same direction with velocities v1 and v2. v1 is greater than v2. When the car A is at a distance d ahead of the car B, the driver of the car A applies the brakes, producing a uniform retardation of A. There is no collision. Okay. So distance between the two cars when the driver applies the brakes is d. This is moving faster with velocity v1. This is moving with velocity v2, and retardation has a magnitude of a. Okay. So this car should not collide with this car. Okay. Let us say after time t, this car and this car just reaches the same position. Just reaches the same position. So what is the critical condition? That this v1 velocity should be just equal to v2 at that time, right? Because then the v1 velocity will keep on decreasing, v2 will be the same, and hence the cars will not collide. So in time t, when they reach the same position, the velocity v1 should have reduced to v2. This is an important statement in this problem. In time t, when the cars reach the same position, at that point in time V1 should have reduced to V2. So basically V1 minus V2 upon T is equal to acceleration. Right now, acceleration or retardation you can say. Okay, magnitude we are equating right now. All right. Okay, so now let us look at distances covered. Hmm? V1 covers a distance of S is equal to V1T minus half A T square. That's correct. And this has to be equal to D plus V2T minus, but okay, there is no acceleration, so we don't need to even consider the acceleration term here. This is it. D plus V2T, that has to be equal to D plus V2T, correct? Okay, and the value of T or the value of A can be substituted over here. The value of T can be substituted from here. T is given as V1 minus V2 upon A. T is given as V1 minus V2 upon A. Therefore, V1 into V1 minus V2 upon A minus half A V1 minus V2 the whole square upon A square is equal to D plus V2 into V1 minus V2 upon A. Alright, so A goes away, all the A's in the denominator also go away. So what we do get over here is V1 square minus V1 V2 minus half of V1 square plus V2 square minus 2 V1 V2 is equal to D plus V1 V2 minus V2 square. Alright, so on simplifying this entire thing, what we do get is this V1 minus V2 the whole square okay. Let me go on to the new page to simplify this actually, because we don't have room over here. So what condition are we essentially using? We are using the condition that when point V1 reaches, this is the point which started with velocity V2, this is point V1, the point that started with velocity V1. When point reaches over here, the velocities just become equal. That is the condition that we are using, and this has a retardation of A. Alright, so basically what we are saying is V1 into T plus half minus A T square. Now this is equal to D plus V2 into T. This is what we are saying. Also V1 minus V2 upon A is equal to T. This we know. Okay. So the value of T we have substituted. So V1 into V1 minus V2 upon A plus half of minus A into V1 minus V2 the whole square upon A square is equal to D plus V2 into V1 minus V2 upon A. So this is d plus v1 v2. So the a's go away, all the a's go away, but then here we have to insert an a to multiply with d, so that a's get cancelled. So this is v1 v2 minus v2 square. Ed is equal to, okay, so v1 square minus v1 v2 plus half of v1 minus v2 the whole square is equal to v1 v2 minus v2 square. v1 v2, when we take it towards this side, it's v1 square minus plus v2 square minus 2 v1 v2 plus half of v1 minus v2 square with a minus sign. This is equal to AD. So ultimately on simplifying we get v1 minus v2 square divided by 2 is equal to AD. Alright, so distance D has to be greater than equal to v1 minus v2 the whole square upon 2a. Only then collision can be avoided. So let us move on to the back page and see v1 minus v2 square upon 2a. What is this option? v1 minus v2 square upon 2a. Distance D has to be greater than v1 minus v2 square upon 2a. Easy concept, easy sum, but slightly tedious mathematically. Alright, this is the solution. Let's move on to the next page. Okay, two particles moving in a straight line towards each other with initial velocities v1 and v2 and retardations a1 and a2 towards each other. Okay, they are moving towards each other with initial velocities v1 v2 and retardations a1 and a2. The maximum initial separation between the two particles so that they may meet. Okay, they have to meet, the particles have to meet. Okay, so what is the maximum value of D? Interesting question again, right? The particles have to meet, so what is the maximum value of D? Okay, so v1 into t minus half a1 into t square has plus, look here, this is an easy question to solve. So this is the distance traveled by the first particle plus v2 into t minus half a2 into t square. Why minus sign? Minus sign is because they are retarding, that's why a2 has negative direction. Okay, so this has to be equal to d. Okay, if they are going to meet, then this has to be the case, correct? If they are really going to meet, this quadratic equation in time t has to have a real root, has to have a real root. Okay, so what does that imply? B square is greater than equal to 4ac. That's correct, no? Yeah. In the quadratic, x square plus bx plus c is equal to 0. So here the value of a happens to be half of a1 plus a2. Okay, this is the value of a over here, the proverbial a. The value of b is the coefficient of t, which is actually equal to minus of v1 plus v2, and the value of c over here is simply d. So what does this imply? That b square, that is v1 plus v2, the whole square has to be greater than equal to 4 times a, which is half of a1 plus a2, 4ac. C has a value d. Alright, so this is greater than equal to 2d a1 plus a2. Alright, so this, right, this is what gives us that v1 plus v2 the whole square upon 2 a1 plus a2. Okay, yeah, simple, straightforward. A particle initially at rest starts moving in a straight line with acceleration a is equal to 60 plus 4 meters per second square. Okay, so acceleration is equal to, this is very simple, 60 plus 4. So velocity is going to be equal to, the particle is initially at rest, so at t is equal to 0, v is equal to 0 has been given. That is given because we need to insert that condition. Velocity is equal to integration of acceleration dt from 0 to t. So this is equal to 6t square by 2 plus 4t. So this is equal to 3t square plus 4t. And you have to substitute from 0 to t. So this is equal to 3t square plus 4t. So that is the velocity of the particle. The distance covered by it in the first 3 seconds is integration of v dt again from 0 to 3. This is the distance covered. Okay, these formulas we have seen earlier how they come. So this is 3t square plus 4t dt integrated from 0 to 3 will give us 3t cube by 3, which is only t cube, plus 4t square by 2, which is only 2t from 0 to 3. So that gives us 27 plus 6. 27 plus 6, right? The distance covered by it in 3 seconds is actually 33 meters. Comes out to be 33 meters. 33 meters is closest to 30 meters here. Yeah. So this is the option we have to take. Okay. 19. A particle is projected with a velocity v0 along x-axis. The deceleration on the particle is proportional to the square of the distance from the origin. Okay. So this is a very important concept that we are going to learn in this problem. Here we are going to learn that acceleration can be written as v dv by dx. Very important concept. Very important for problem solving. Acceleration can be written as v dv by dx. Alright? Because acceleration is equal to dv by dt, which using the chain rule of derivatives we can say is dx by dt. Okay? Into dx by dt is nothing but v into dv by dx. Okay, dx by dt is v into dv by dx. So acceleration is equal to alpha x square. This we know. Okay, so v dv by dx is equal to alpha x square. Therefore, v dv is equal to alpha x square dx, right? Integrating this from 0, initial projected with velocity v0, it's not 0, it's v0, okay, along the x-axis, and this is v, the distance at which the particle stops. So the final velocity is 0, right? Integrating this from v0 to 0, and this is 0 to x, correct? Those are the limits of integration. Cool. So therefore this is v square by 2. This is v0 to 0, so this is like minus v0 square by 2 essentially, is equal to alpha x cube by 3. Okay, so we have to take the magnitude naturally because distance has been asked. So taking the magnitude, 3 v0 cube upon 2 alpha raised to 1 by 3 is the distance x, right, at which the particle stops. So which option is that? Option D, right? D is the option. The correct option is D. Okay? Yes. Yeah. 20. The acceleration due to gravity on planet A is 9 times the acceleration due to gravity on planet B. A man jumps to a height 2 meter on the surface of A. What is the height of jump by the same person on planet B? Okay. So when a man jumps, what happens is his initial velocity u is converted into height, correct? Or you can say kinetic energy is converted into potential energy. Kinematically speaking, we have to use the equation 0 because at the highest point man has 0 velocity, no? Right? So 0 is equal to u square plus 2as. So here 0 is equal to u square plus 2 into minus g into h max. Therefore, h max is going to be proportional to u square upon 2g. U, the initial velocity with which the man jumps, depends upon the leg strength of the man. So u is going to be assumed to be constant. So h max is basically u square upon 2g. So h max 1 upon h max 2 is equal to g2 upon g1, right? It is inversely proportional to g. So this is easy to understand. So g2 upon g1 has been given to be 9. Acceleration due to gravity on planet 2 is 9 times that of Earth. So this is 9. So h max on Earth upon h max on planet is equal to 9. Therefore, okay, we are assuming that okay, A or HA upon HB, A and B, they haven't given Earth and other planet, they have given HA and HB. So HA upon HB is equal to GB upon GA. Okay, so GA is said to be 9 times, so it's 1 upon 9 actually. So HA upon HB, that's a more convenient way to do it. HB has been asked and HA has been given to be 2 meters. So HB is equal to 9 into HA is equal to 18 meters. Alright, easy question again. A body falling from high minaret travels, okay, a body falling from a height basically travels 40 meters in the last 2 seconds of its fall. The height of the building, height of the minaret is what? So basically there is a building over here, a body has been thrown from the building. We have to assume that it has been thrown from rest. In the last 2 seconds it travels a distance of 40 meters. Okay, let us say we have to assume that it fell for t seconds. So s is equal to half gt square, right? But in the last 2 seconds, how much can it travel? Half g t square minus half g t minus 2 the whole square, right? Because it got time to travel this much in the last 2 seconds. This much has been given to be 40. From this, actually we have to find out the value of t. Alright. So how to solve this now? Okay, so 80 divided by g is equal to t square minus t minus 2 the whole square is equal to t square minus 2t plus 4 is equal to t square goes away, 2t minus 4, that is 80 by 10. So 8 plus 4 is equal to 2t. So 8 plus 4 is 12 by 2 is 6 is equal to t. It takes 6 seconds for the body to fall. So the answer is going to be half into 10 into 36. That is 18 into 12. Half into 10 into 36. The height of the minaret in meters is 40 meters. 18 into 10. The answer should be 180. This option should be actually 180. 180 is this option, okay? Because look here, 40 it fell in the last 2 seconds, right? So total time of falling is t. So half gt square minus, before last 2 seconds it had fallen this much. So 2 I am taking towards this side, g I am taking below. So that's 80 by g. 80 by g is 8. 8 is equal to t square minus t minus 2 square. So that's t square minus 2t plus 4. So t square goes away. This is 2t minus 4. Okay, and this is 8 right here. So 8 plus 4. 8 plus 4 is 12 is equal to 2t. T is equal to 6 seconds. You substitute t is equal to 6 seconds here. You should get the answer. The answer comes out to be half into 10 into 6 square, that is 36. 36 by 2 is 18, into 10 is 180. There is no option like 180 over here. 180 should be one option. That's the answer. Alright. Three different objects of masses m1, m2, m3 are allowed to fall from rest and from the same point O along three different frictionless paths. The speed of the three objects on reaching the ground will be of the ratio of what? They are allowed to start from the same point O and they have to reach the ground, okay, along three different paths. Alright, these are frictionless paths. So basically what is going to happen, the speed of all the three objects is going to be, no, we'll have to see, this potential energy mgh is going to be converted into kinetic energy, right? Half mv square. This is not really a kinematics problem, but we'll solve it anyway. Okay, and this mass gets cancelled, right? So basically the velocity with which they reach the ground is independent of mass. So v is proportional to under root 2gh. So that is the same for all. So the answer is C. The velocity is the same for all. A man throws a ball vertically upwards. It rises through 20 meters and returns to his hands. What is the initial velocity u of the ball and how much time t it remains in the air? Okay. So the maximum height reached by the ball, this is motion under gravity, right? The maximum height reached by the ball is 20 meters. Okay. So basically, which equation do we use? U square minus 2gs is equal to 0. We use the equation v square is equal to u square plus 2as, right? So this is equal to u square, 0 is equal to u square minus 2 into g into 20. G happens to be 10. So 20 into 20, 400 is equal to u square. So u is 20 meters per second. For how much time t does it remain in the air? Very easy to answer. Okay, v is equal to u plus at. Okay, this is the time t of ascent t. That is going to be the same as the time of descent t. Okay, ascent and descent will take same time here because they are symmetric. Okay, so 0 is equal to 20 minus 10t. So t is equal to 2 seconds, that time of ascent. So total time is going to be equal to 4 seconds. So these are the answers. T is equal to 2 into 2 is equal to 4 seconds. So this is the answer, D. Very easy again. The time taken by a block of wood to slide down a smooth inclined plane 9.8 meters long. Angle of inclination is 30 degree. Okay, this plane is 9.8 meters long. Okay, try to do this question. It's easy. What is the acceleration? G sine 30 degree. This is the acceleration. So s is equal to 0 into t, because initially it's at rest, plus half into g sine 30 into t square. So 9.8 is equal to half into 9.8 into sine 30 is half into t square. So this gives us t is equal to 2 seconds. Simple. Next question. A body is projected up with a speed u and the time it takes to reach the maximum height. Okay, t is the time taken to reach maximum height and the maximum height is h. Pick out the correct statement. It acquires a velocity u by 2 in t by 2 seconds. No, it's not linear. Same velocity at 2t. Yeah, yes, because whatever with velocity it is going to be projected with, the same velocity is going to return with, right? Yeah, D is the correct statement. Let me erase firstly whatever I have marked over here. Okay, so D is the correct statement. It reaches s by 2 in t by 2. No, the motion is not linear. Okay, it's a quadratic graph, right? S is equal to ut plus half at square. The motion is not linear, so this is not correct. Velocity is u by 2 at h by 2. No, only D is correct. Only D is the correct answer. Next. PQR are three balloons ascending with velocity u for u at u. If stones of the same mass be dropped from each when they are at the same height, then okay, so this is easy to answer. The stone that is going up with a velocity u will go something like this. Okay, the stone that is going with a velocity 4u will go something like this. The stone that is going with a velocity of 8u will go something like this. Alright? Yeah. And they have asked ki which stone reaches the ground first. Okay, so let us try to use a general equation. Initial velocity, let it be u, t plus half to minus g into t square is equal to height, right? Height is the same, they have been dropped from the same height. Okay, so basically what do we get? Multiplying by 2 we get t square gt square minus 2ut, okay, plus 2h is equal to 0. Which time is going to be least, they are asking. Okay, so the value of t depends upon the value of u in this manner. 2u plus minus under root b square minus 4ac, right? Yeah. 4u square minus 4 times 2hg 2hg upon 2g. Alright, this is the case. Okay, negative answer we will discard because that will give us a negative value, negative solution, right? Correct? So you can see over here that the time is proportional to u. This u will come outside and this time is going to be proportional to u. So whichever has higher velocity will reach quickly. So that is, this guy will reach quickly. Yeah. Okay. Okay. A frictionless wire AB is fixed on a sphere. A very small spherical body slips on the wire. Time taken by this ball to slip from A to B. What is the time taken by this ball to slip from A to B? See, g sine theta is the acceleration, right? G sine, okay, the acceleration is actually g cos theta because this theta has been, see, look here, mg is here, no? And theta is here, so acceleration is actually g cos theta. And this distance AB, is 2r cos theta, right? Yeah. So actually we'll get a surprising result now. This time taken is independent of theta because 2r cos theta has to be covered. Okay, so s 2r cos theta, this is equal to half g cos theta into t square. Okay, cos theta goes away, so 4r by g, the root of 4r by g is equal to t. 2 root r by g is equal to t. Easy to understand. Option B is correct. Next question. Okay, this is, we are in the last couple of questions actually. That's it. Three particles A, B and C are thrown from top of a tower with the same speed. Again this question is the repeated question, right? Okay, it's not exactly repeated because they are thrown in different directions. Yeah. A is thrown straight up. A is thrown straight up. B is thrown straight down. And C is thrown horizontally. They hit the ground with speeds VA, VB, VC. Alright. So this is VA, this is VB, and this is VC. See, VA is going to be equal to VB. Why? Here time is not been asked. Because of energy conservation, when the particle goes up like this and comes back to this point, right, it is going to have the same velocity. Am I correct? Yeah. So it is as if VA and VB are being thrown down only from this same point. But for C, that is not the case. For the point C, the velocity of C is directed like this. Alright. So it will have this velocity component and it will also have a velocity component, okay, that it has gained because of acceleration due to gravity. Okay, let us say u is the velocity because of which they are thrown. So here the final velocity v is going to be equal to v square is equal to u square plus 2gh. All right, correct. So c will have the velocity component in the downward direction as root 2gh and velocity component horizontal as u. So its vector addition, the vector addition of both the velocity components will give it, this is true for va and vb. The vector addition of c's velocity component at the bottommost point will give it u square plus 2gh. So we get a, you know, slightly intuitively surprising result that all three are reaching the ground with the same velocity. That is the answer A. But if we think about energy conservation, this result is not really surprising because all three of them have been projected with a velocity of u. So when they reach the ground, their potential energy will be converted into kinetic energy, right? And since that, so initial kinetic energy was equal, so final also has to be equal for all, meaning final velocity also has to be equal for everybody. The last question. Two bodies are thrown simultaneously from a tower with the same initial velocity v naught. One vertically upwards, other vertically downwards. Distance between the two bodies after time t is. Okay, interesting question. See here, distance. Okay, there are two methods to solve this question. Method one is this. This is a tower. One body is thrown vertically upward, one is thrown vertically downward. Okay. So how to calculate? The upward body has a displacement s as ut plus half into minus g into t square. The downward body, this is s1. The downward body has a displacement as minus ut because it's thrown in the negative direction, right? Plus half into minus g into t square. So s1, okay, actually to get relative displacement we have to do something like s1 minus s2. So s1 minus s2 is ut plus ut, right? 2 ut, correct? So this is method 1. 2 ut is this answer B. Method 2 is realizing that they don't have relative acceleration, and when they don't have relative acceleration their relative velocity remains constant. Important statement again. When relative acceleration is 0, when relative acceleration is 0, relative velocity is constant. So what is the initial relative velocity? U plus u, 2u, right? So 2u is the initial relative velocity. So s is going to be equal to 2u initial velocity into t. S is the separation between them, plus half into relative acceleration is 0 into t square. So this is just 2 ut, which is in our example 2 v naught t. Okay, so B is going to be the answer. Okay, easy. Okay, with that we end our basic introduction to one-dimensional kinematics. Thank you.